I'm Guo Cheng Guang, 11 years old, primary 6, from YUMIN Primary School. For this time, we'll continue to revise our methods of limit calculation. In our methods of limit calculation, for these lessons, we will take a look what types of methods we might meet along the way. To help us understand these methods and how we can use them together with other methods, we will use examples, many different types of examples, and we will also explain how can we use these, and for sometimes why we cannot use it like whatever methods. Let's start these examples. For the first example, we have limit x approaches to 0, bracket 1 over x squared minus 1 over tangent square x, bracket. This is the first example that we have. These different types. We first have to check which type of form is it, determinable or indeterminable. When you sub 0 in, you get infinity minus infinity. So that's the indeterminable form. Infinity minus infinity. That means we cannot straight away sub the x in. So we have to use different types of methods to help us try. Let me try a bit. Can we first try to common denominator? Well, we have to try it out. If we first common denominator, then at the numerator in this part is tangent square x. Therefore, the other part is minus x squared. Now, what do you think of this? Something square minus another square. Well, I think it reminds you of a square minus b square. So a square minus b square, you'll get tangent x plus x, then tangent x minus x. Then over this denominator, we let it be the same first. Then what can you see from this part? What form is it right now? At the numerator, 0 times 0. At the numerator is a 0. Then the denominator is also 0. This is the indeterminable form, 0 over 0. What can we find here? Now this tangent x plus x. Is there any changes we can make to it? Well, it seems like we can try. Now this tangent x here, I think it reminds you of the special limit. Because tangent x, if you divide it by x, it can become a 1. And if you divide both of these by an x, then you have 1 plus 1. And that gives you 2. So I'll try this. Now when you divide both of these by an x, that means it's actually taking one x from the denominator. So in the first bracket, tangent x over x, then plus 1. Then behind, we can also let it be the same first. So this square don't have. This part, we can already find that it's a 2. Then limit x approaches to 0. But how about for that tangent x minus x at the numerator? That might be a little bit more difficult, so maybe we put it later. But how about the tangent square x at the denominator? Now tangent square x at the denominator, you could also use special limit number 1. So you can times x squared over x squared. Now this part, you'll realize it becomes a 1. So we don't have to write that down anymore. Then this tangent x minus x, then over the x cubed. Now at this part, we can separate it into 2 different methods. From here. Well, both methods, this first part is all the same. The first method, tangent x, we could try to change it using the Maclaurin series. Let me tell you for tangent what is it like. So tangent x, when you use the Maclaurin series, it becomes x, then you have to plus. Now this part, you can write it as a 1/3 x cubed, like this, or you could also put x cubed at the numerator. It doesn't matter. Then you have to plus 2 over 15 x to the power of 5. And you have to know this. The Maclaurin series, there is infinite terms. That means it keeps going on. So this is a Maclaurin series for tangent. Let's first try it in. Let's take a look. Here, minus an x. This term don't have. This is still here, but you have that over x cubed. So it becomes 1/3. Then plus 2 over 15 divided by x cubed. So x squared. Then all the way. Now what do you realize? All the terms behind, because this power 1, 3, 5, 7, and so on, it keeps on increasing. That means all those behind, they'll all have x to the power of something. Now with the x to the power of something, you can use direct substitution. All those behind is 0. That is 1/3 here. And the answer you get is 2/3. Then how about the second method that you can separate from here? Now this second method is a little bit different. First part, 2 limit x approaches to 0, tangent x minus x. Now this tangent x, we could use the L'Hopital's rule. So tangent x, it will become secant squared. Because for L'Hopital's rule, it is numerator and denominator, you differentiate them. Okay, then here minus 1. And then over, now x cubed is a 3x squared. Now here you have another method. It's either you change this, like for example, okay, secant square x minus 1, you can change it into tangent square x. Then after that, it becomes sine square x over cosine square x. Then you find it. Okay, let me just tell you. This numerator, it becomes tangent square x. Okay. 3, you can take it out. Like this. Now tangent square x, change it into sine square x over cosine square x. Okay, so this method that I want to use, I'm just trying to say you could use this special limit again. This part becomes 1, then behind down here is another 1. So the other answer is still 2 over 3. But if you don't want to continue it like this, you could use L'Hopital's rule again. But for this sine square x, it'll get a little bit more complicated. So these are the two methods that I use here. Okay, so this is tangent x minus x over x cubed. So that means in this infinity minus infinity, 1 over x squared is bigger than 1 over tangent square x by 2 over 3. But then, this tangent x, you might think of, in this trigonometry, is x something special about it? Okay, let me tell you what this x has to be. So this x, it has to be in radian. And for example, this is a unit circle. Then from this unit circle, if we say this is its center, you can have its radius. For example, these two are its radius. And this circle, what's so special about it? We can call it a unit circle. That means this radius is just 1. Since in this, we just need its ratio. So even if it is 2, well, we just want its ratio. And this angle is the x. And we say here is O, A, B. Then we'll draw a line down. And it's perpendicular. And this point, you call it C. What's so special about AC? This line AC, here's the right angle, so it's a right angle triangle. Then you have the cosines and the sines. Oppo, you have that sine. So this is sine x. Since its hypotenuse is actually just a 1, so you don't need to write that. But what if, like for example, here we want tangent. What if we say it's a tangent that we want? Now tangent is the opposite side and the adjacent side. Now, this, we could take this as the adjacent. That means it will become 1. Then like this. So this is still a right angle triangle. And for example, if we call this point over here D, if we call that point over there D, now this adjacent, opposite over the adjacent is a 1. So that means tangent x is actually dB, like this. Now you have AC and you have dB. Okay, later on we'll continue to find what's so special inside here. Okay. AC, these two. Then you might have a question, how about this arc? This arc, AB. For this arc AB, this has to be in radian. So that means it will just be this angle times its side or its radius. So it's just an x. Well, at last, I'll tell you why would I want to write this out? Okay. So can we just put this aside first? And we'll continue with our second example. Since in this second example, we have to say about the sine. Okay, now we have this tangent. Okay, so we'll take a quick look at this first. Okay. With this second example, you have limit x approaches to 0, then bracket 1 over x minus 1, here you have a square, yep. Then sine square x. This example, let's first check what type of form is this. So in 0, infinity minus infinity. Still infinity minus infinity. Now how about we try the same method, because for sometimes different types of questions they just change one part. You can still use the same method. So let's try that method again. Now you have limit x approaches to 0, common denominator, so at a denominator will be a x squared sine square x. Then the first part, sine square x minus x squared. What kind of form is this? Sub in 0 is 0 over 0. Another type of indeterminable form. And this part, factorization using a squared minus b squared. Until this part is still 0 over 0. Then the next. What can we try to remove from here? If you divide by x for both of these, it's still a 0, since it's just a 1 minus 1. But how about for the other part? You get a 1 plus 1, yeah. So let me just write it out what it will be like. That gets us that 2. So we could divide this by x. And that means we actually take one of these x from the denominator, give it that. And it becomes like this. Now here's a 1 plus 1. And you'll get a 2. So 2 as a constant, you can put it in front of the limit. But how about for inside here? Sine x minus x over x sine square x. We could also try to first remove this sine square x just by times x squared, then you divide x squared. So this part, special limit number 1, it'll give us a 1. So that part, we don't need to care about it. Then here inside, maybe we write it as the same first. Okay, and also at this part is when we start to have two different methods. Method 1. We will again use Maclaurin series, but this time is for sine x. So let me tell you what it will be like after that Maclaurin series. So sine x, this now is a bit different. At first it's still x, but after that it's to minus 1 over 3 factorial this time. It's not a 3 anymore. But here is still x cubed. Then plus 1 over 5 factorial. Then x to the power of 5. Then you minus. So you'll realize this is alternative now. Positive, negative, all the way. But for all of these Maclaurin series, they all have infinite terms. So let's try to put it in here right now. To limit x approaches to 0. Then part x minus x becomes 0, so don't have. And then here, minus 1 over 3 factorial. But x cubed, simplify with x cubed. So we don't have that. Then plus 1 over 5 factorial. Divide, you have an x squared and minus all the way. Then you also realize all those terms behind, you also have x. Now with all of these having x, you can direct substitution. And then you just get this part at the front. So it's a negative. Now, this 3 factorial is 1 times 2 times 3. So 2 can simplify with that. And it's a negative 1/3. Let's check using our second method to see whether is it right. The second method, L'Hopital's rule. So this part, okay, now it's a little bit simple. Differentiation. Sine, you get cosine. Then x becomes 1. Then down here. Then you get cosine x minus 1 over 3x squared. But if you want to use the method of using L'Hopital's rule again, you can also use it. Well, let me just show you what it will be like. So if you use L'Hopital's rule again, okay, you could actually take this to the front, and then you'll realize this part is special limit number 1. You have negative 1/3, so it's still the same. And what does this negative 1/3 mean? It means, now which one is bigger? So it's this part that is bigger, 1 over sine square x. Now this 1 over sine square x is bigger than 1 over x squared by 1/3. So don't just think this is infinity minus infinity. Sometimes we could still find what are the differences between these two infinities, or what is their actual difference. Just like these, they're just fixed numbers. Okay, and let's just finish up that last example. Now this last example is something special, and it's actually something that we have done before. So I'll just put a sign here. And this is the limit x approaches to 0, in bracket 1 over sine square x minus 1 over tangent square x. Let me tell you a trick. You don't need to go and common denominator again. Just this tangent square x, you become sine square x over cosine square x. And then you could actually get the same denominator. That is sine square x. Then up here, 1 minus. From this, you get an actual cosine square x. Then you get sine square x over sine square x. And that's a 1. That means the differences between these two is a 1. Or 1 over sine square x is bigger than 1 over tangent square x just by 1. Although this is still infinity minus infinity. But something special about this is actually, this is a trigonal identity. For fixed numbers, yes, this is 1. Even for 0, still a 1. Okay, if you still want to continue with this, let me explain about this. Now, we have already found for the sine, the tangent, okay, x is just there. Let's take a look. AC. Can we look at their relationships? Now, which one is bigger? Which one is smaller? AC. Is it bigger than AD? Well, of course, no. Then how about AB and DB? Well, actually, AB, it is smaller. Am I right? Okay. Now we get this kind of thing. But how about we try to solve this in? Now AC, what you get is a sine x. Now sine x. How about this x inside here? Is this sine x smaller than the x? Okay. Then after that, this part, for the dB, there is a tangent. This is smaller, but then inside these questions, you might think it looks a little bit wrong at first. How is this smaller? But actually, in this question, we have this reciprocal. So when its denominator is small, its fraction is bigger. So 1 over sine x is actually bigger than 1 over x. And 1 over x, ever smaller than tangent x, becomes bigger than 1 over tangent x. It's just that in these questions, we have an extra square. So even from these, we could find out which one is bigger than what. Okay. And that is actually what I want to write about these. Okay, so in these 3 examples, I hope that you're clear so far. And if you like our videos, don't forget to subscribe to our channel, so we'll see you in the next lesson. Last but not least, thank you for your watching.